Facebook AI research in Paris. I joined Facebook 1.5 years ago. And since then, I've been working on academic research in the field of computer vision, machine learning, and artificial intelligence in general. So today, I'll tell you a little bit about the general principles of building and training neural networks, and also how these kind of things are exploited in Facebook products, and also what kind of research we do at Facebook. A bit more than a year ago, at our annual developer conference F8, Mark Zuckerberg presented a 10-year roadmap for development of the company. And you see that here, after the first short-term plans for improving and tuning the core apps, such as Facebook, Instagram, WhatsApp, Messenger, there are also a number of more large-scale, more ambitious projects. So first of all, that's connectivity. These are all efforts around connecting developing countries to the internet. So that's everything which concerns satellites, drones, lasers, and so on. Also here you see Oculus. So this is everything around augmented reality and virtual reality applications. And or here, right in the middle, there's a group of projects which are dedicated to development and exploiting AI technologies. So the general goal of this group of projects can be formulated as creating an intelligent agent, which could, which could help to facilitate communication between people and also interaction between people and machines, such as computers or robots or whatever you can think of. So this time there is a number of groups which are working on machine learning for Facebook products. And our group, which is called Facebook AI Research, or FAIR for short, its mission is to perform more fundamental research in the direction of development artificial intelligence technologies. So we do purely academic research. We publish all our results in conferences and journals. We try to make all our open source for the sake of reproducibility of the results. So everyone anywhere in any academic lab could take these results and further improve them. Our lab was created 3 years ago, and the director of FAIR is Yann Lequin, who is a French scientist, and he's often called one of the fathers of deep learning. I'll tell about him a bit later today. So at this moment, there are more than 100 members in our lab, both scientists and research engineers, coming from 20 or 30 different countries. And at this point, we have 3 main locations in New York and Menlo Park in California, and in Paris in France, where I come from. And there are 3 smaller groups in Tel Aviv and Seattle and in Montreal in Canada. The Montreal lab will be expanding soon. So let me tell you a little bit about how it all has started and what are the general ideas behind deep learning. And today I'll be focusing mainly on computer vision aspect of things, because that's where I'm personally working on. So if you look at statistics of the most frequent words used in computer vision research papers in recent years, you'll see that a lot of them are coming from literature on neural networks. And probably the word of computer vision today, it's ConvNet, which stands for Convolutional Neural Network. So let's see what's the idea here. Sorry. Before deep learning came into field, that is roughly before 2012, all computer vision pipelines were built roughly in the same way. So for example, in the classic setting of supervised learning, we have some input X, and our task is to map it to some output Y. So in computer vision, input X is typically an image or a video, And the task can be, for example, classification, where Y corresponds to one of discrete labels from our set of predefined classes. Or it can be a regression task, where Y is a real value or a vector of real values. For example, if we want to identify the edge of the kitten. In a computer vision, there can be more complex tasks based on two classification and regression elements together. For example, increasing resolution of the image, or semantic segmentation, or pose recognition, or whatever you can think of. So before 2012, most of these algorithms are built based on two independent stages. So the first one was so-called feature extraction, which was based on extracting handcrafted engineered descriptors, which typically reduce the dimensionality of the input and at the same time make it easier to separate, for example, different object classes present in images. So those descriptors formed intermediate representation X prime, and this intermediate representation was used as an input to some classifier or regressor, or in general case, some machine learning algorithm, which was used to perform the task. And parameters of this machine learning algorithms were optimized for a given purpose. So the problem with this approach is that those engineered descriptors D can be basically anything. They were created and tuned and improved over years and even sometimes decades. And the problem is that they needed to be adjusted for every kind of data input, for every kind of task. And once a task changes, we need to start everything all over again, which is not practical and just does not scale to all sorts of applications you can think of. Instead, the idea of deep learning is to perform end-to-end learning of those representations, one or typically a sequence of representations together with the final machine algorithms which actually performs classification or regression. This idea was initially inspired by neuroscience because, well, we roughly know that brains contain some neurons and the connections between them. And also there is a known property of the brain which is called plasticity. And neuroscientists showed that the same parts of the brain can adapt for processing different kinds of inputs depending on changing conditions of the environment. So the first goal in deep learning research is to make these models biologically plausible, that is to create some sort of approximation of the actual brain. Those models typically have from thousands, typically hundreds of thousands or million parameters. And to train them, we typically need the same order of amount of training samples. So we need to collect huge data sets for all tasks we can think of. We want to create general models which could be used to process any kind of input and solve any kind of task without much human involvement for adjusting the models. And also we want to perform all sorts of learning, including supervised and supervised reinforcement learning, and so on. Okay, that was what we want. What we actually have now is something which is loosely biologically inspired. And in reality, we still don't know how brain works and still very, very far from approximating it in any meaningful way. We have a huge amount of training samples for some small subset of applications. For example, you know, we have lots of images from internet, which is nice, but at the same time, for example, in medicine or in astronomy, the amount of data is not at the necessary scale yet, and this data is expensive to collect. These models are way more general than we used to have, but at this point, we still usually need to manually optimize the structure of neural networks and to put some effort into training them. You know that supervised learning is now in product pretty much everywhere, but at the same time, unsupervised and reinforcement learning are still work in progress and mostly a subject of academic research. You probably heard that even though deep learning became fashionable right now, the field is really not new. And the first works on deep learning date back to 60s, when Soviet researchers in process control created first works on neural networks. And the second wave was in the middle of 80s, when Yann LeCun and Geoffrey Hinton invented what we call today backpropagation, which is an algorithm for training neural network, basically very close to the one which is used today. And as I already said, Yann LeCun, who was one of the inventors of backpropagation, is a director of our lab today. Okay, but even though most machinery was invented in 2000s, in 80s, at that point, the big success was not really achieved because there were several factors missing. We did not have enough computational resources to train the model, we didn't have enough data, and also the techniques for training these models were not yet optimized. So these problems were more or less solved only by the end of 2000s, when we got GPUs, multi-core CPUs, and lots of data. So in 2011, there was first breakthrough in speech recognition from Microsoft, and in 2012, first very important result in computer vision from Geoffrey Hinton's group. So one of the main factors of success of deep learning in computer vision was creation of a huge collection of images collected from internet, which is called ImageNet, and which was a project at Stanford. So what they did is they collected 14 million images and annotated more than 1 million of them manually using crowdsourcing. So since 2010, Stanford proposes an annual challenge for object detection recognition localization based on some subset of these images. Typically, they take 1 million images, 1,000 classes, and let different teams to compete on those tasks. So before deep learning, the best results that was achieved correspond to 26% error. This was in 2012. And the first neural net, which is called AlexNet, on this task reduced the error to 15%, which according to computer vision standards, it's a huge improvement. This was something unheard of and basically a revolution. In the next couple of years, the error was going down. And of course, the question here was how this performance of 6%, for example, compares to actually human performance. So a couple of years ago, there was a PhD student in Stanford, Andrei Karpathy, who performed this experiment, and he personally took all this data and spent a month just to learning these images from ImageNet and corresponding class categories. And after a month of training, he was able to perform classification with 5% error himself. And even at test time, he was able to look up training samples to find something the most similar. So the general observations here were that people are still worse than machines in fine-grained recognition. For example, for us, it's very hard to recognize 100 breeds of dogs. And also, it's hard to memorize everything we have observed. At the same time, deep neural networks have problems with images which are processed with filters, photoshopped, and so on, when objects are occluded or too small or blurred, for example. And of course, both make mistakes if the data is just not right. So human performance was first surpassed in 2015 with ResNets from Microsoft. So we went from 6 to 3%. And this year, the best performance is roughly 2% error, which you see basically, yeah, much better than humans. Okay. So as I said, the 3 factors of success of deep learning in these years were computational resources, a huge amount of data, which typically what companies have. And for academic research, it becomes increasingly more difficult to advance in this field. So sort of revolution here started in 2011 when Andrew Ng founded Google Brain project, first dedicated lab which worked on deep learning at scale. Then Jeff Hinton went to Google a bit later. Then in 2013, Facebook's AI lab where I'm working at. And then in 2014, Google acquired DeepMind, which is a company performing fundamental research in AI as well. And if you look at statistics of participants of scientific conferences on machine learning, deep learning in particular, you can see that there are more and more people coming from companies such as Google, Microsoft, Facebook, Amazon. This was a couple of years ago, and this year, for example, at NIPS, they were expecting 6,000 to 7,000 participants, mostly coming from companies and startups. Partially because the conferences will be located in California, but still the statistics is impressive. Okay, for those who are not closely familiar with principles of how neural networks works, I'll spend a couple of minutes on covering those. So the very basic unit of every neural network, this is something which we call perceptron, and basically it's a single layer, a linear network. Here we have some input x, which is mapped to output value y, and y is computed as a linear combination of inputs with some weights w. Plus we have some, so basically it's a weighted linear combination plus some constant which is called bias, which corresponds to the value of y when all inputs are equal to 0. As I said, this is a basic unit which is not very interesting in itself. But this is something a bit more complicated, but it's actually already used in practice in some cases, which is called logistic regression. It's a non-linear single-layer net. And the difference here is that at the output, we have not a single value, but a vector of values, which have certain semantic meaning. For example, if you want to perform a classification into 1,000 objects, at the output we'll have a vector of 1,000 values. Each of them will be proportional to probability of finding the object from a given class in the given image. And this network is nonlinear, and the difference with the previous case is that the final activations are calculated as some nonlinear function applied to the weighted linear combination. This nonlinear function is called activation function, and it can take different forms. The very, very basic case is binary step, which is close to Heaviside function. Another one, which is sigmoid or hyperbolic tangent. This one was very popular for decades, partially because it really looks like something which is happening in real neurons in our brains. Because we know that real neurons have sort of linear part over here, and then they tend to saturate. But in modern system, the activation function which is most widely used is so-called rectified linear unit, or ReLU, which looks like follows. And these networks, these activation functions are very fast to compute. And they also solve some typical problems of training, such as attenuation of gradient, for example, vanishing gradient. The same pattern of neurons connections and activations can be repeated several times, and this way we construct a multi-layer network. So here, for example, we have a 2-layer network with input, output, and something which is called hidden layer in the middle. To train such a network, first we need to calculate the difference between the output activations and actually ground truth values. This can be done given some arbitrarily defined metric, but in the simplest case, for example, can be linear or quadratic difference. This difference is called loss function, and the training procedure is basically based on calculating the gradient of loss function given all parameters of the network. So we need to calculate partial derivative of loss function given every weight in the network, starting from the output layer and moving to the input layer. And then using the gradient descent algorithm, we basically adjust all values of all parameters in order to minimize this value of loss function. This is something which is called back propagation, and as I said, it was invented back in the 80s. So from theoretical point of view, the 2-layer or 3-layer network which we saw just before is already sufficient to approximate any arbitrary complex function y of x up to arbitrary level of precision in theory. But in practice, it means that we may have to add an infinite number of neurons into our hidden layers. And these networks are just very, very hard to train. And typically, there are no theoretical guarantees that they can actually be trained. In practice, it appears to be much more efficient, effective, to create deeper neural networks with stacked layers. Each of them is basically much narrower in this case. So here we arrive to something which is called fully connected deep neural network. In the context of computer vision, fully connected networks are very rarely used, or basically not used, because first they have way too many parameters. For example, if we have 1,000 dimensionality 1,000 in the input, and then 1,000 neurons in the hidden layer and 1,000 outputs, it means that we already have 2 million parameters with this very, very basic net. So these networks are, I would say, wasteful or redundant, and also they do not generalize well because they are something which we call not special invariant. Basically, it's shown over here with the example of monkey, and these fully connected nets will produce different responses depending on where in the image the same object is located, which is not what we want. We just want to say that it's a monkey. So instead, in computer vision, as I said, the V word of computer vision is convolutional neural network, which is before a linear operation, but this time it's local. So multiplication by matrix in the previous case here is replaced with convolutional operation. And the idea here is that we scan our image with a number of filters which share weights with each other, and this way we obtain the same response given the same patterns regardless of where in the image they are present. So this is strict definition of discrete convolution. It's probably familiar to those who worked with, I don't know, optics or signal processing and so on. Yeah, I will not go into details here. So in ConvNets, the operation of convolutional, the convolutional operation, at least in the most basic networks, is typically followed by something which is called max pooling. Max pooling basically reduces the resolution of the obtained feature maps. So feature maps, that's the output of convolutional layers. Their dimension is reduced. This way, we're able to extract features at different scales given several layers of the network. And at the same time, they give us more degree of special invariance because we basically can move the object a little bit around the image and it will not change the response of the network. So the same pattern convolutions plus max pooling can be repeated several times to form the deep network as before. So that's max pooling. And at the very end, we can have a number of fully connected network layers which produce the final results. But it really depends on the application. Some applications, we only have convolutional layers till the very end. So this is a short video of something which is called LeNet. So that's the first convolutional network created at Bell Labs in '93. And what it was doing is recognition of handwritten digits. So again, this is Yann LeCun, who is a director at Facebook now, Facebook AI Research. Here is an illustration of how depth of these networks was evolving over years. So in 2012, when AlexNet first won ImageNet, that network had barely 8 layers. When we surpassed human performance, it was ResNet, 152 layers, And now there exist methods for training networks up to 1,000 layers. But to be honest, the difference between hundreds and thousands at this point already not that significant. So one of the most important questions at the very beginning was, of course, what do these networks learn and how our learned filters actually look like. So if we look closely at the filters learned at the very first input layer, the first after input convolution layer. So here I show you the filters, and these are the patterns in the input image which activate those filters most. So you see that in the very first convolutional layers, we basically have borders with different orientations, which are almost linear. At the second layer, we have something looking like geometric primitives. One more, something more like textures. If we move further, layer 4, we already have something which looks like images. So for example, over here, we learned something like a dog face detector, which is really activated on dogs. Oh yeah, so it was a couple of years it was everywhere, which is something called deep dreaming from Google. Probably you saw that. So the idea here was to create some sort of psychedelic illustrations or videos from pre-trained deep neural networks. And what people were doing is basically just taking a pre-trained net and adjust the input in the way that it increases the response of one or another filter. Basically, if we know that in this network, dog filter is already firing, we want to adjust the input to make it fire even more. Sorry. Yeah, so this is an illustration what happens if we start activating more of those filters starting from the very beginning. So if we want to increase the edges in the image, we modify the input to activate the edge filters at the very input. And then we move to like geometric primitive filters, which increased, then textures, and then you'll start seeing eyes everywhere because these will be eye detectors which activate it. Okay, I don't want to hypnotize you here. I'll move. All right. There is also a number of properties of neural networks which are very interesting and which we need to be aware of if we want to use these neural nets in practice. So for example, a couple of years ago, there were a couple of papers showing that something which is called adversarial examples. So the idea here is that if we have a pre-trained network and some inputs which are correctly recognized by this network, so we have a dog, a car, or so on, so we can construct some very small distortion, almost random noise, which is added to the original input and which is almost unperceivable by humans. And this will cause the network to make errors and to be not just producing erroneous predictions, but to be absolutely confident in them. So the network which is confident in dog now is confident in ostrich. That's Strauss in Russian, if someone doesn't know. Yeah, so the idea is basically very simple. To obtain those adversarial examples, what we need to do is to calculate the gradient of the output, not with respect to network parameters, but with respect to the input image. And then we just need to adjust the input image just a little bit. And the error will accumulate over the network. It will sort of resonate and drastically change its prediction. So this property is somewhat interesting from just theoretical point of view, but also it poses threats for security, because this way we can actually attack neural networks and make them believe that they're seeing something which is not actually there. So for example, if we talk about semantic segmentation framework, which could, for example, be used in autonomous driving setting. So we have an input image of a road, and the network is trained to segment it, that is, detect people, cars, and so on. And we want to attack the network to modify the input just a little bit to make it predict something completely different, to suppress all humans or cars and just change the prediction. And it's actually very easy to do. So the input will be looking roughly the same, but the prediction of the network will be like this. And this works even with the most abstract targets. So for example, if we have a pair of input prediction for normal healthy network, and we want to fool the network into predicting something like that, so this is basically the same segmentation map. So the head here that's basically model cycle class, some traffic signs class, and so on. We can modify the input such as it looks like that. Very similar, but it's actually, we increase the noise to show the difference. And this will be the network's prediction. Yeah, so if you want to use neural networks and applications which are kind of critical for human life, you really need to think about protecting those against these kind of adversarial attacks. Okay, and in practice, there are still lots of issues that you need to think of if you want to train your own neural net. First, get enough data. If you don't have enough data, think about how to increase the amount of data artificially. So this is something we just call data augmentation. And in computer vision, it typically means that when we train our network, we want to take different crops from images, do some sort of rotation, scaling, and so on, to actually increase the amount of training samples. We need to normalize the data correctly, typically to something like 0 mean unit variance. We need to carefully optimize architecture. So for computer vision, it's at least the basic architecture is more or less known, but if you have completely different application, you'll need to think about what kind of architecture is the most suitable for that. You need to think about loss function, which can be basically anything, but you can start with a set of the most known ones. You need to think about weight initialization. There are a set of standard practices as well, but it's kind of important for the speed of convergence of neural network training. Again, training hyperparameters, including learning rate, schedule. You need to think always about overfitting, which is especially crucial if you don't have enough data again. So think about regularization methods or early stopping. And then there can be different update rules for gradient descent. You can think about using Atom or MSProp or, for example, momentum to speed up the training. Okay. And finally, to finish this tutorial, let me briefly mention what happens if you have not just images, but for example, sequential data. So it can be videos or something more complicated in different applications such as text, phrases, and so on. So for video, if you just want to recognize instantaneous actions, we can do something very simple. Just extend the dimensionality of our convolutional filters, and instead of 2D convolutions, do 3D convolutions and 3D pooling, or potentially combine both 3D and 2D vectors. This works if the action can really be recognized from a very short movement, but if we need to model longer sequences, this will not scale. As in this case, the network mostly just memorizes what kind of instantaneous motions it has observed. So once the capacity, like the modeling capacity of memorization is reached, you will not be able to generalize to new patterns. So this is basically, yeah, just illustrated by this image saying that if something changes, like these kind of networks do not actually learn the movements, but they learn the impression from movement. So if you change your hand, if you change your leg, it will not generalize to this kind of case. So a better idea probably, and to achieve better generalization, is to use temporal models of short long-term dependencies. So the very basic architecture is a recurrent neural network here, which is again known for decades now. And the difference here is that, so if, as before, we have a fully connected deep neural net, which is now shown vertically for different moments of time, t-2, t-1, t. So the difference is that in addition to feed-forward connections, at this time we also have connections between timestamps, which are called recurrent. This is the very basic architecture, which is actually rarely used in practice. And to do something more practical, there are networks which are called LSTM, long short-term memory networks, which also have some memory cells to represent this temporal information accumulated over time more efficiently and to prevent the network from forgetting those. But here is an example, here's an example how temporal models can be used, say, to predict what kind of symbol will come next in the text in a phrase, just as a toy application. So this network was trained on Tolstoy's War and Peace. It just saw lots and lots of texts from this book, and it learned what kind of symbols come after each new symbol. So after 100 iterations, it outputs complete mass. After 500, it kind of learns the concept of words and spaces between them, punctuation signs, and so on. But the text still doesn't make sense. And after 2,000 iterations, it produces something which looks almost meaningful. Yeah, so at least the grammar is correct. If you don't really pay attention and look super closely to it, it looks good. And if you add more data to it and keep training for longer and longer, it will be able to produce perfectly valid phrases, which are maybe not very interesting and original, but statistically it will represent the training texts quite well. Okay, so I'm done with the first part, which was tutorial. And in the second part, I'll cover what kind of applications and what kind of research we're doing at Facebook with that. But I think we'll stop here for a short break or questions if you have regarding this part. Thanks. Yeah, any questions? Okay, if no question, then let's resume in like 50 minutes. Yeah?
How exactly do you protect your image recognition networks from this noise sensor?
It's an open research question. Technically, there are no methods which would guarantee you this kind of protection. So it's basically really new direction of research. And you can, well, the very basic thing you can do is to actually use this kind of adversarial samples just as a part of your training data. Yeah, just to learn this kind of, just to prepare the network. But in general, there are some more serious architectural changes should be done, and it's not solved. Yes. Yeah, sorry, just don't people actually see your model, because to attack the network, you need to know the structure of the network. So don't release your models if you have these kind of crucial applications. Yes?
Yeah, that was actually my question. So if I don't publish my model, it would be impossible for attackers to really build these noisy images that would compromise the result. Or it's not true?
Yeah, well, okay, so if you have the model, it's obvious. The next step would be if you have, for example, not the model, but if your service is open and everyone can, for example, on the internet upload their images and get their predictions. So you can, if you have an opportunity to use this model for a massive amount of data, you can actually collect your own data set of your model's responses to my own data, and then train a network which would be kind of close imitation to what your model does. In this case, there's a hope that samples which are adversarial for my model will sort of be adversarial for your model. So certain loss of performance, of course. There are lots of There are lots of experiments on how on testing these samples transferability, and it actually shows that for models which are not that performant and more or less simple, the adversarial samples which are adversarial for one model often also work for others. It's not that crucial, but you will still hurt performance of many other models, regardless of their architectures and data they're trained on. Yes?
Do you use a network-in-network model? I mean, like a hyperhook network to recognize some errors or calculate fitness points to recognize some modification in net or misplaced data sets?
To recognize, you want you want to do sort of classification like adversarial, non-adversarial?
I mean, do you use like in prediction algorithms, never evolutional augmented topologies? It's kind of different networks.
So the question is, do we need them?
Okay. You build your own network and train.
Yeah.
Like accumulate some information without losing.
Okay.
And if you do you use some other networks to extract some information and modify your pre-training network?
Okay, so you say that if we have a network.
I mean, if you have an mistake or error in your data set, another network can extract these errors and solve it, for example.
Okay, so the typical pipeline, for example, have a network which is pre-trained on ImageNet. Then you take the same network, apply it to your new data set, which will make some errors, right? And then, yes, you can fine-tune this network, which is pre-trained on something else, to achieve better performance on your own data set. Yeah, it's definitely common practice, because if for the new application you don't have enough data, it certainly makes sense to pre-train it on something else, such as ImageNet or other different, typically ImageNet, but depends. Yeah, and then just fine-tune the output layers or the whole thing end-to-end on the small amount of data which you have and which is specific for your own application. Yeah, it will help to reduce error. Yes?
When you're talking about examples like this in which you start seeing like good results after like, I don't know, 1,000 iterations,
Mm-hmm.
like what kind of methods or techniques do you use to know that you should stop iterating? Because I imagine at some point the results will be really similar and don't change that much at all.
Yeah, so here you basically have a very simple notion of error, just comparing predicted symbols and ground truth. So, well, first you can stop when you see that your error saturates, like plateaus, and you can say, okay, if for a certain number of iterations there is no change, let us stop. And at the same time, if you have a problem of overfitting, so if you don't have enough training data, then you need to control your error both for training data and for validation set, which is like hollowed out subset of data, and then see what kind of behavior the validation error demonstrates. So typically it will go down, 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 and then once the network starts overfitting, the training error will keep going down, and the validation error will start again to a plateau or even eventually go up a little bit. So the point you want is the one corresponding to the minimum validation error. Yes? I don't hear you, I'm sorry. Okay, well, I believe there are certainly news, but I personally don't work on that, so I don't want to speculate on something which I'm not really closely familiar with. I believe there are lots of people who do this kind of FPGA networks and so on. It's not my field. Anyone else? Yes?
Hello, Dalia. You are working now in a research department and Facebook.
Mm-hmm.
Are there some plans to convert it to some kind of business in future? What is the practical plan?
All right. So for now, the lab is very young, and it's for such a company as Facebook. It's very experimental because for now we do not necessarily profitable. So for now there are no plans. The plan is to advance technology as far as we can, and if we see that some of our works can actually be practically applied to some of Facebook applications, there are dedicated groups which actually make it into product. So we don't need to convert our labs. There are other labs at Facebook that can pick it up from us and then to convert something useful. Our goal for now, at least for upcoming years, we'll see in the future, but for now it's research. Anyone? Okay, then. Yeah, yeah.
You work on Facebook and you collect some information about conversations with people and predict some. Do you have a network to predict some, let's say, conflicts in conversations with people? It's like some prevention about some people can hurt.
Yeah, so this does not exist as a product, but there are certainly people thinking and talking about that. So there can be a number of directions. First, yes, suicide prevention or detection, I don't know, prevention of terrorist attacks if people are talking about such things. Or the next step would be creating a bot, for example, which could help you if you have any kind of psychological problems, right? So this bot would be imitating what like basic psychologists would tell you if you're depressed or, I don't know, upset, or if something bothers you. In this case, yes, first the bot could talk to you and maybe calm you down, and at the same time it could maybe send some alerts to people who care about you that you're actually not doing well. Yeah, this is something that we're thinking about maybe in future. Anyone? Yes?
Does exist any approach to combine several neural networks? For example, I've got a very huge collection, and I, for example, can separate it into to make learning faster. And after that, I want to combine these results, like like in case I learned on a whole collection.
Okay, so you want to split the model into simpler models, or you can split your data into subsets.
After that, I want to combine it. Does exist any approach to do this, or something like this, for example?
Well, certainly there is nothing really complicated, but you know that most of competitions on Kaggle on machine learning are basically won by ensembles. When people train lots of basically networks with different random seeds, with different subset of data, with slight modifications in architecture, and then for actual competition at test time, they take predictions from all these networks and basically take an average, or yeah, you can think of like average mean or geometric mean, but typically just the average gives you reasonable results. So that the error of ensemble is basically always better than error of single network. It's just in practice, it's maybe not really meaningful because you don't want to have 100 nets in your applications because it's just slow. You need lots of memory and so on. But it gives some boost in performance, of course. Yeah, I don't think there's a like strictly correct answer to that. What's better, to have a network which is really huge and trained over a long time, or having a number of those which are smaller, but you have several of them? It's a trade-off, but yeah, you need to experiment with that. And if you have hardware limitations for training, you can certainly try that. But yeah, there's no like formula saying how many networks you need to imitate performance of larger network or something like that. Okay, that's it? Yes.
Mathematical equation, and while people are thinking what to ask on that subject, I think that it would be interesting to attend this. What kind of background you have? Where have you been studying?
My background.
Your background. You are for 1 year in Facebook now.
All right.
Or in Paris. You definitely speak French, I suppose, too. You came to this point.
Okay, so like,
Talk a little bit about
yeah, my biography in 2 sentences. I graduated from MGTU имени Baumana in Moscow. My first degree was in optics and electronics. After that, I did a master's degree in computer science. It was Erasmus Mundus program in France and Norway. So basically there I studied computer vision and machine learning. Then I did a PhD in France on computer vision again. So I defended in 2016, I guess. My PhD was partially in France, partially in Canada, and I also spent 4 months at Google as a visiting researcher working on a project in the field of security on mobile devices with deep learning. So their idea was to take motion sensors such as accelerometers, gyroscopes, and so on, and basically create a deep neural network which would be able to process this kind of signals and to authenticate the user on device just based on the way you move, something like that. Yeah, and after that I joined Facebook. That's it. Thanks. Okay, I guess that's it for the first part, so let's take a short break and then we'll continue with applications. So there are, of course, lots of ways how we could organize our research in artificial intelligence, but we like to cluster them somehow in 4 major groups, even though they are very closely connected to each other. So the very first one is perception, or what I usually call computer vision. That's where I work on, and that's where I'll be focusing mainly for the rest of the talk. The second group is understanding and learning. And here the idea is to create networks which would be able to perform basic reasoning, not just recognition, but maybe higher level reasoning, have some sort of, I don't know, intuition and general knowledge about this world. The third direction, prediction. So if you want to build an agent which would be able to help you with some tasks, to anticipate the future events, the agent need to actually have a sense of what's going to happen next. So this is a particular case of what we may call prediction learning or predictive learning. And finally, planning. This is something which follows prediction. So this is something about reinforcement learning. So I'll talk mostly about perception, and then at the very end, I'll briefly mention the main points for the rest of the groups. Perception. So there are lots and lots of directions in computer vision which you may want to work with. And especially at Facebook, we have huge amounts of data which are collected around humans. So it's mostly images of humans, video of humans, everything about humans. And we are interested, for example, in human detection or action recognition or pose estimation in 2D with skeletons or directly in 3D. You can also think about recognition from RGB images or from depth maps and also from motion capture data, such as, for example, the one given by Kinect. You can do recognition and perception at the scale of whole body, or you can do, for example, gesture recognition and hand pose estimation specifically for close range interactions. But of course, there are lots of even higher level applications about social recognition of social interactions, making sense of them, and so on. So the progress in computer vision is being made very rapidly these days. So in 2012, when we had AlexNet, basically what we could do best is just to assign the single label to the image and say, okay, this image contains a person. A couple of years later, we're already able to indicate the regions belonging to different objects and to extend our vocabulary. And at this point, we can do it quite well. So you see the localization is quite precise, and we have lots of object classes. In addition to basic detection localization, we can do also other tasks, as just, for example, pose estimation. So here is a demo of the network, which is called Masker CNN. This is the state-of-the-art in object detection with masks. So here, for example, the network is applied to a video frame by frame. Those frames are independent, and we do not take into account temporal dependencies between those. So if you actually do some kind of temporal smoothing or modeling larger term temporal dependencies, you can further improve performance on top of that. But even this works already quite well. Yes. The same kind of architectures can be deployed to mobile devices after some compression or simplification. So it runs in real time on basic Android device or iOS device. And yeah, the performance is quite good. So the basic idea of all, okay, not all, almost all, I would say mainstream detection frameworks, it's built upon two logical steps. If you want to detect multiple objects in an image, first what you want to do is to use some sort of deep neural network, or convolutional neural network, to generate so-called proposals. Proposals are regions which are candidate where the network is assuming that there are some sort of objects, regardless of what classes that they belong to at this step. So this is done over a dense grid, and we have a number of templates or anchors. For example, you may say that at every point in your grid, you can have an object of one of three sizes. For example, large one, middle one, or like medium one, or a small one. And also the object, for example, can be square or elongated, or it can be vertical. And then at each point at the grid, you output probability of locating object of a given size, a given orientation at this point. And you also output adjustment coordinate for the bounding box with respect to the template. This works quite well. So the object is generating proposals, which are then used for recognition and, for example, to generate precise object masks. So here what we do is we take features from every region and then process them separately to output the final label or mask, or, for example, pose if the object is a person. So the proposals that do not actually contain images first filtered out, since they will have probably low probability of having an object, and also if the object is not recognized, the proposals are also removed. And here you see, for example, performance of this kind of network for street kind of scenes. It successfully can initialize lots of instances belonging, for example, to the same class, but it can still tell the difference between objects. Okay. Yeah, sorry for that. I don't know why it's doing here. Yeah. Next important task, human pose estimation. So here the idea is to, for every person in an image, basically localize positions of some key points which typically correspond to skeleton joints. So the idea is basically the same. First, we detect people, and then for each region corresponding for a person, we perform pose estimation. Pose estimation can be formulated as detection of these key points, but at this point, we know that normally there is a single key point of a given class in an image, so the task is formulated a little bit differently. So this is almost state-of-the-art framework from Carnegie Mellon University. This is not a Facebook actually method, but it works almost as well as Moscow CNN. It's basically just to show you, to give you an idea of quality of the state-of-the-art. Another task, which is probably ancient in computer vision, face recognition or face verification. Basically, given two images, we need to say if it's the same person or not. So in 2000, I think, yeah, 14, yes, 2014 group from Facebook for the first time surpassed human performance in this task. They improved precision by 27%, and this time the network could tell that this is Nicole Kidman, this is Nicole Kidman, and these two pictures actually belong to a different person. So now you can see that face recognition is everywhere, like people telling Tom Hanks from Bill Murray, but for the first time it was done this level of performance in 2014 at Facebook. So now we're interested more not just in face, for example, recognition, but in localization some facial points, and performing pose estimation for faces and for bodies densely. This is very important, for example, for better understanding content of an image, but also for augmented reality applications. If you want, for example, crop a person from one scene, insert him into another, give some objects, attach some objects to it, you need to really understand what's the body parts and so on. So for example, for dense pose estimation for face, this is the most universal dense representation, which can be then used for any face-related task you can think of, like localization of facial landmarks, or segmentation, or anything like that. Yeah. Okay, yeah, so that's basically the same thing. And we do the same thing for full body pose estimation. Again, for multiple people, you can basically, given a single image, you can map every point from an image to sort of virtual 3D model of a person. Yeah, so dense pose estimation. As I said, these representations are the most complete and the most useful for any kind of task you can think of. But the problem with this kind of networks is that you actually need ground truth data, which is collected exactly in the same form. And this is difficult because you cannot ask people to take million images and just densely annotate all points in a body. So important direction of research here is how to collect this kind of data automatically to reduce the cost of it. So for example, at Carnegie Mellon University, again, they created a huge setup, which is called Panoptic Dome, I think. It's a kind of semisphere where they put lots of cameras inside, about 500 VGA cameras, some, I don't remember the number, but some substantial amount of high-resolution cameras and also depth sensors. And the idea is they put a person or a number of people inside the sphere, and they film them with these hundreds of cameras. And those videos and all these views can then be used to triangulate the position of every point and to correct predictions of state-of-the-art pose estimation frameworks, and to use these corrected predictions to retrain them for better performance. So here, for example, you can see how it works for hand pose estimation. So this is predictions on a single view, but it was trained using multiple, using training data collected with multiple views. And it's very significantly outperforms all state-of-the-art results that were created before that. Yeah, a couple more results over here. So it's actually very robust, and even given that the image is dark. Yeah, so once again, this is Carnegie Mellon University work. But now at Facebook, we have the same setup, which was actually even improved. And the authors from Carnegie Mellon now joined Oculus Research to work on these kind of problems. Okay, another direction of research, which interests many are sort of maybe practitioners of deep learning, is how to create networks which would be useful for different sorts of applications. Because of course we're always limited in memory, and yeah, we want to create a universal network. So for example, given the same image or same video, what we want to predict is, for example, object detection, so like all people, cars in the street, or we may want to segment. Yeah, we may want to segment the scenes. Sorry. Anyway, we may want to segment the scenes or extract boundaries surrounding objects, or for example, detect human parts, like here, or estimate orientations of normals of surfaces in a scene, which is a very low-level task. So here, for example, we also detect saliency of objects. It is the objects that attract the most human attentions, and people look at it. Borders again, yeah. So if we have first lots of different data sets that come with lots of different annotations, for example, I don't know, semantic, segmentation, detection, borders, and so on, we may also want to create a universal network which would be able to learn from all these differently formulated sources of information using different subset of data. And one of the important engineering challenges is how to construct such a network that would fit in a memory, and also how to combine these tasks efficiently such that they would not degrade performance of each other. Because, for example, we know that, say, semantic segmentation and body part segmentation are highly related to each other, so they may help to each other, but at the same time, maybe, I don't know, normal estimation is quite relevant for this task, so we'll take some part of model capacity for something which is not actually useful for us. So the challenge here is to build or even automatically learn the structure of the network, which would learn to assign its parameters, its capacity to different tasks and combine them in an efficient way. Because if we don't think about it carefully, we'll run the scenario something like that, where we have a single network over here and lots of managers that ask it to do different tasks. And of course, the final performance may degrade. Yeah, so this is, for example, output of UberNet networks, one of the first attempt to do something universal. And it can output 8 sorts of outputs at the same time, which can be used for different applications. Okay, another very popular direction of research over here is solving inverse task, not recognition, but actually image synthesis. And for this, people use something which is called adversarial neural networks, which were proposed by Young Goodfellow a couple of years ago. And according to some people, this is probably the most important invention in the field of deep learning in recent years. So the idea is actually very similar, very simple. We're given some random noise vector at the beginning, which is passed to a neural network which is called generator. And what this generator does is it learns to generate some sort of image. So the task is to generate realistically looking images, of course. Yes, once these images are generated, there is another network which is called Discriminators. And this network as an input takes 2 subsets of images, where the first one is a subset of generated images, and the second one is a set of real images. And this network is trained to discriminate between them, to detect which is which. And this combination of 2 networks is trained jointly in a sort of game setting until they reach an equilibrium point. So at the very beginning, we adjust parameters of discriminator to actually teach it to discriminate 2 kinds of inputs. Then we calculate a gradient. We calculate the derivative of the discriminator error not only with respect to parameters, but also with respect to the image, just as what we did for adversarial samples. So for example, then we inverse the gradient over here and backpropagate it for whole parameters, the whole set of parameters of generator. So basically, the generator in this case is trained in such a way that it maximizes the error made the discriminator. So in simple terms, we train the generator to fool this discriminator into believing that we generate real images. And this way, we actually increase the realism of generated content. So the first more or less working framework was proposed at Facebook a couple of years ago. So you can see that if you look at these images from a distance, they look like they actually cropped from some, I don't know, natural, almost natural images. But if you look at them more closely, you can see that, okay, we more or less capture statistics of natural images, but actually there are no details, and strictly speaking, it's not super realistic. Yeah, so what actually works better is to give them more context to this kind of network. In this case, we would not ask them to generate just any image, but for example, image of a given object, or we can go even further and to ask it to generate something very specific. Like for example, over here, we may say that, okay, we want to generate a church under blue sky. So we provide this information, we encode this information for generator and also for discriminator. In this case, part of the input vector would contain this encoding of the condition information, and the second part would left to be random, just to have some variability in our generated input, generated images. Because, for example, we may want to have lots of different images of churches on the blue sky. And the same information is given to discriminator, so now it doesn't only tell realistic, non-realistic, but also corresponding to the description or not corresponding to the description. And here's an example of state-of-the-art performance on this task. That's again not Facebook work, but we're doing something similar. It's just they had nicer images. So for example, if we ask the network to generate a yellow bird with some more details on color and structure, so it looks much better than before and higher resolution. Same, it can generate pink flowers. But if you ask something maybe more abstract or, I don't know, more complicated, it kind of works, but not quite if you zoom in again. So these guys do not actually look like cows, like kind of, but these are sort of zebras, but, well, you know. Yeah, and another thing to, another important detail to make it work is that actually these frameworks are now multi-stage. So first you generate low-resolution image, then feed it to the next stage, and then just learn to add more and more details into your generated output. Yeah, and yeah. Okay, so there are several directions where you can go from here. But for example, if you remember, we had a random noise vector in the input. But what would be actually more interesting is to actually understand what this random noise vector contains to be able to control different parameters of the generated input, right? So we want to each element in this vector to be sort of responsible for certain attribute in the image, which we actually can interpret and understand. And from another angle, we can say that basically what discriminator part of adversarial setup does is that it learns to, well, basically, okay, in their collaboration, what they achieve is to removing some sort of information from generated outputs. So for example, in the classic setting, we remove some sort of artificial artifacts to match image statistics, right? Or you can formulate your discriminator not to tell difference real, not real, but for example, if your discriminator is a classifier and you want to fool it, basically you want to create an object which the discriminator network hasn't seen before, right? So it would not be able to tell its class. So based on this idea, there was a recent work which is called fader networks. So given an image of a face, we pass it into encoder. Encoder is just certain network which performs certain transformation on the input to produce some intermediate representation, or as we say, latent representation E. And then, okay, yeah, I'll tell you what it is in a second. Just let me show all of it. Yes. Right, so the first part of it is encoder and discriminator, and here we fool discriminator into not knowing particular attribute of the face. For example, if we, if we have attribute whether the person is wearing glasses or not wearing glasses, we want to create discriminator which would not actually know that, right? So this representation would contain some essential information about person, but not some sort of superficial details on what he's wearing today. And then these artifacts which are removed from these representations can be encoded separately in a binary vector. And these two representations together can be then passed into another network, which somehow learns to combine them to output a new image. So if over here we put exactly the same attributes as we have in the input, we would just learn to reconstruct what they had at the very beginning. But for example, if this person is not wearing glasses, but here we set binary attributes for glasses to 1, we would want to output the same person, but with glasses. And you can do it for any kind of attribute, basically removing any information from the slide representation, just contain information about the general appearance. So some results here. So these are 3 input images. For example, if you want to change the gender, yes, it kind of preserves the identity but changes the gender. Or yes, it could make them wear glasses, or open eyes wider, or make them older or younger, and yeah, open or close the mouth. Yeah, so you can basically think about anything, any sorts of transformations you want to learn. Another application for adversarial networks, more or less the same setup, can be, for example, domain adaptation. If you want to create an avatar for from your photo, you can train a network which would preserve some information about your face structure, facial features, but it would basically not know whether it's a photo or a sketch, and you can easily switch between them. Yeah. And the last applications over here, the same idea, but to create something which we call creative neural networks. So basically here again we have generator and discriminator, and what discriminator does not know is what kind of art style the painting belongs to, right? So the idea here is to create a completely new art styles which do not exist at this point. So this is what makes the networks creative. All right, we covered the main directions of computer vision. Just a couple of words. Okay, it does not look well. Laptop charge a bit, so I'll just talk to you because, okay, for the next direction research, we don't necessarily need slides. Yes? Супербомбических. Меня же уволят. А записывают. Нет, well, okay, I think the projects that I'm talking about today are more or less representative of what we're actually working on, so it's not like I'm hiding from you something very, very different from what I'm telling. Okay, so yeah, let me just continue, okay? All right, yeah, okay. Yeah, so the second direction after perception is learning and understanding. So the idea is here, as I said, we want to teach networks to do some basic reasoning and to incorporate knowledge about the world. So there can be several setups on how you can do that. For example, a couple of years ago at Facebook, they created a data set which is called Baby Tasks, and it contains short stories, a couple of sentences long. Like, for example, I don't know, Bob went to a kitchen, Jane came from the kitchen, and Jane put a cup on the table. And the question is, where's the cup? Or something like that. So you can construct this kind of short stories for different sorts of reasoning. So you may ask the network to count something, or to reason where the object is, or to do some kind of translations, like, I don't know, swans are white, John is a swan, is he white, or something like that. Yeah, so there were 20 different sets of tasks, and at the point where this data set was created, none of existing neural architectures can actually solve those. So a couple of years ago, at Facebook, they proposed something which is called memory networks, which was able to solve half of them, and at this point, there's something which is called entity networks, which can handle all 20 tasks. 1 second. Okay, so the next step after baby tasks was something called children books dataset. And the idea is that given a short story, but not as short as before, so I don't know, 20 sentences, basically a fairy tale or a very simple book for children, the network is supposed to read it, and then it's given another sentence at the end with some missing word. And the idea is that it needs to fill out the word. So it's more challenging task, but still state-of-the-art architectures can do that. More or less, they perform well if the missing word is basic, I don't know, basic term or verb or something like that. But if it's a name of a person or a place, it has some problems with that. No, okay, I think it's not coming back. I'm sorry. Yeah, and today's most interesting, most challenging task is something which is called open world questions. Basically, the setup is the following. We asking the network to answer any open world question. For example, I don't know, how many people spoke Polish in Warsaw in 1840, something like that. Completely open. And what the network is allowed to see is basically the whole Wikipedia. Well, you think it's easy, it's actually really not. It really isn't. So the very first step, the network is supposed to find, to retrieve all articles which can actually be relevant to the given task, and then it reads them, scans them, and finds the most relevant term. Yeah, so this is basically the state-of-the-art interaction of reasoning. Okay. Third group, predictive learning. So there can be two goals why we may want to do predictive learning. First, as I said, to literally predict what's going to happen next. And the second one, it can be seen as some particular form, it can be seen as a method to do unsupervised learning or self-supervised learning. For example, if we have a video, we can extract different frames corresponding to single images, and then use the image which comes right after that as a sort of supervision for the given image. Right, so basically we learn to predict next frames, and the idea is that if we're able to do that, we actually taught the model to understand something about dynamics of the world, about entity of objects, geometry of the scene, and so on. So this is basically a way to learn data representations without requiring any expensive human annotation. You can also extend this concept not necessarily to prediction in time, but say you can take one image, cover half of it, and you need to predict what is missing given the input which you can actually observe. So we work on different directions in this field. For the literal task of predicting future events, for example, you can do it directly by predicting pixels and future frames, but this is very difficult because there's lots of variability, and apparently the network just does not focus on the actual task, it's just overwhelmed with all these pixels. What is maybe more interesting is to do it on a bit higher level of abstraction and just to learn how the objects will be moved around the scene, not necessarily caring about their colors and textures and so on. So first we perform semantic segmentation, and then we train the network to predict how the segmentation will be changing over time. So this is something which can be used, for example, in autonomous driving again. If you have cars around you, you may basically see how they're going to move, and in a perfect case, predict a distribution of their future trajectories to anticipate and to adjust your driving. All right, and the fourth group, which is probably the third from what I'm working on, this is planning. And for doing research and planning, what is typically used is called game AI. So people literally train the networks to play games because it's kind of controlled, well-defined environment. And if you can create agents that can reason about those environments first, then we can actually transfer something to robots to navigate in more realistic settings. So first, people worked on basic games like Tetris, where it's fully observable and there's no actually adversary in the game. The next step was playing Go. So maybe you heard a couple of years ago, DeepMind released the AlphaGo framework, which actually won against the world champion. At Facebook, there is also some research in this direction. We actually proposed something for playing Go before DeepMind, but it was trained on much smaller amount of data. It's basically much more compact framework. It does not perform that well, but still it does a reasonable job, and it's used somewhere, I don't remember, in Korea, I think, to actually train kids at school to play Go. And the next step would be playing Doom, where still, yeah, the action space is kind of limited. You can go straight, left, right, and you can shoot. But still, at this point, it's your environment is not observable anymore, and the action can be just more. The planning is more complicated because of that. And yeah.
About OpenAI and Dota winning that
Yeah. Right. There's a lot going on about game I agree with that. Yes. Yeah, probably Facebook here is not actually the leader. Yeah, but this year we won competition for Doom bots, and last year again. So yeah, there's a lot going around that. And yeah, the highest level of complexity for today is probably playing StarCraft, where you have a huge action space, huge state space of the system. You have lots of agents which need to cooperate, action together, and this is probably the most challenging task for game AI, for reinforcement learning, and for planning. Okay, of course there are lots of directions of research which I did not talk about, say machine translation, speech recognition, and so on. But I think we more or less covered the main strategic directions for next years. So thank you. Questions? Yes.
Yes. Regarding the first part when we were talking about perception, when you start like to having the generator and the discriminator, I assume that the discriminator neural network cannot be very smart because it would reject basically every image that you pass to it. So how do you establish the perfect point to start for the generator and the discriminator so that not everything gets rejected and that these images are not too bad like to be like always rejected also?
Yeah, okay. In practice, actually, discriminators do learn to perform this classification almost perfectly, at least at the end of the training, and it's basically not a problem. If you state something like, I don't know, 95, well, not, okay, for binaries. If you're staying still at a level close to chance, you still can get some useful signal, even though discriminator is pretty good. So you never actually fool him, but still you get some signal of direction where you need to tune your parameters to increase this error a little bit. There are different strategies for balancing those networks. So you of course you train them interchangeably. There are people who are trying to put different learning rates for them. Apparently now it's not recommended, but at some point people were doing that. You can actually prevent. You can try to prevent saturation of your network, so you don't initialize your labels to 0 and 1 for real, non-real, but you can have something like 0 and 0.9. So for real images, the network is trained to be confident that they are real, but not too confident. So it kind of prevents it from going to perfect performance real quickly. But again, adversarial networks are still very, very tricky to train, and there's a lot of research going on just around how to make the procedure more efficient and how to prevent them from crashing and, yeah, make it in a more optimal regime. Yes?
Are you using it from building from scratch, or you're supported by some frameworks or libraries?
Adversarial nets or everything?
Yeah, for neural networks and for planning and stuff.
Well, okay, so at Facebook, we're internally developing PyTorch and Kafka2. So we have engineering teams which support and develop those, and I think most of our researchers actually using those just for sake of compatibility, and because we actually believe that these are good platforms. So PyTorch is as it's clear from its name. It has a Python front end, and it's really convenient for researchers who want flexibility and ability to customize their models. Kafka 2 is more production framework, which is way faster and much better optimized for performance and for speed of training conversions. So if you want to do something like detection and localization, you may want to switch to Kafka 2 directly, just because it trains roughly 1 day to train state-of-the-art detection framework. Yes? Sorry. What? Yeah, baby, yes, it's called B-A-B-I. You can see Bobby, baby. Yeah, okay. Yeah, you can certainly do that, and I think in the past, before deep learning, people were certainly doing that. So the idea here is that we do not explicitly enforce any grammar constraint or any language structure, and the network is supposed to first learn what is a verb and where is the subject implicitly, if it needs it, if it's actually optimal strategy, and then to sort of parse these phrases and memorize terms which may be relevant for the given question. So we assume that the network actually does it in some implicit form, but we do not ask the network to do that. You can do it in, well, it's I think at this point it's trained on English, and to train in English is tested in English, but yeah, you could, in theory, you could do it for. Well, we need to solve the task at least for simple grammars first, and then we can think about it. Yes?
I know there is a trend when they are doing electronics designed for custom tasks, like the microchip, which is designed for learning neural networks, are using such hardware acceleration.
No, well, thanks. Yeah, okay. I don't think that it's really a Facebook priority for coming years, and it's definitely not priority for our group. So in our group, we're not working on optimizing neural nets for hardware or hardware for neural nets. That's really not the level. Yes?
What kind of model do you recommend if someone wants to classify grade of brain tumors according to MRI images?
Well, okay, I'm not working on medical images myself, so maybe there is something specific for the task. Well, my general guess would be to start with something like ResNets, or there are lots of segmentation frameworks which are based on convolutional deconvolution layers, where you basically can process information in multiple scales. So you need to recognize or segmented? Just recognize?
Classify. Like
Just
classify by grades of malignancy.
okay. Well, I guess the first thing would be just to take ResNet, like residual neural network, and tune it for your task and see what it gives. But yeah, but I really don't know the specific literature here. Yes? Yes? Yeah, of course, we have a research cluster with, I think it's a couple of thousands of GPUs for now, where you can, researchers have access to that and can launch jobs in parallel. There are certain people who are working on extreme parallelization of those, like training recognition frameworks on ImageNet in 1 hour and so on. In this case, you would need not only parallelize across GPUs, but you would you would need parallelize across machines. In like everyday research, we typically don't do parallelization across machines. So typically it's like 8 GPUs, and it's enough for training most of applications. Maybe not for production, but at least for research.
Another question. When you create a network training, to give a best result, you need to minimize hardware cost. Yes? You decrease layer. How you optimize the network? The main thing.
Well, if you have certain memory constraints, well, again, it's more like engineering challenge, but you can do something which is called knowledge distillation.
I mean about parameters in network. How it decrease in the right way.
Well, okay, that is what I was trying to say. So, for example, if you have a huge network which is working really well on your task, but for some reason you cannot fit it on your phone, for example, what you may want to do is to take a smaller architecture, just literally smaller, less layers and so on, and train it not from scratch for the task, but instead to mimic the output of the actual large network, right? So your ground truth here would be not just a single layer, a single label per image, but the whole distribution of probabilities over all classes, which is output by the large network. So this way you are given some sort of richer supervision, and this way you can actually train even smaller model with, of course, some loss of quality, but you may actually train it to mimic the performance of the large net quite well. Yeah, I don't know in terms of numbers, but for example, that's what we did for Masker CNN. So I showed you performance for Masker CNN on this like jumping guide that was a real large network. The mobile version of it can still quite robustly recognize masks, but sometimes it flickers, and yeah, positions of key points are not so stable. So you can visually see it, but it still does a reasonable job. Okay, should we, that's it? Okay, so we don't have time, I guess. Yeah, we need to go. Thank you.